factorials, or as I like to call it, the most exciting thing in math. It's a really bad math grammar joke. All right, so a lot of people sort of remember factorials, right? They don't really come up in Calc 1 at all, right? But we need to make sure we understand what factorials are and how we algebraically manipulate them, because they are going to come up a lot. A factorial is another piece of a sequence that you can't just take the limit for, not directly, right? We have to do a little bit of algebraic manipulation. So a factorial, if I write in factorial, what this is you start at 1 and then you multiply it times 2, then 3, all the way up to the value n. So if I had 3 factorial, it would be 1 times 2 times 3. If we had 4 factorial, 1 times 2 times 3 times 4, okay? So you can see why, if you had a factorial in a sequence, trying to take the limit of that could be a little dicey. Now, if I just say what's the limit of n factorials, n goes to infinity, hopefully we all see that's going to blow up to infinity, right? So that's pretty obvious. But we want to make sure if I put it in the denominator, if I have 1 over n factorial, that's 1 over infinity, and everybody would say 0. Well, what if I mix that factorial up with some other stuff? Like, how does the factorial, does it outpace an exponential? Does it grow bigger than a polynomial, right? You have to know what's happening there. So let's just review really quickly a couple of quick algebraic moves we can do with factorials. So if I write n plus 1 factorial over n factorial. So the denominator is saying start at 1 and multiply all the way to n. The numerator is saying start in the numerator, multiply all the way to n, and then multiply by n plus 1, right? Because you go one number past. So, excuse me, n plus 1 factorial is really just n factorial times n plus 1. So it makes sense if we put some real numbers in there. So let's say that n is 5, right? So the denominator is 5 factorial. That makes the numerator 6 factorial. So 6 factorial, 1 times 2 times 3 times 4 times 5. There's your n factorial times 6, okay, on the outside. So these n factorials cancel, and you just get n plus 1. So when you stack 2 factorials on top of each other, look for the one that's bigger, and all you have to do is grab the extra terms. That's it. And everything 1 through the first term will cancel, all right? So let's look at, right, n plus 2 factorial. Well, this says go all the way up to n, and then you multiply by n plus 1, and then n plus 2. So this is how you write consecutive integers when you're indexing, excuse me, from another integer. So once again, if n was 5, right, if n is 5, then this is 7 factorial. So this says we'll then go to 5 factorial, multiply times 6, multiply times 7. So you can take a factorial and split it up, all right? So what we use this for, a lot of times in math, what we commonly, in statistics, and you guys don't really get to see this, but this is a cool party trick, right? We use this to find combinations of things. So how many different ways can you select 0 items from a group of 5? So I have 5 candy bars in a bag, and I tell you you're going to randomly select n candy bars out of the bag, okay? But you draw the number 0 so you don't get any candy bars, right? So the question is, how many ways can that happen to you, right? And the answer is actually 1. There's only one way you can get nothing. You just get nothing, okay? If I said, how many different ways could you select one candy bar from the bag? Well, there would be 5 different ways. You could have grabbed the first one, or you could have randomly gotten the second one, the third one, the fourth one. So there's actually a formula for this. And the notation we use, right? We say 5 choose 0, right? So it's I have 5 things, but I'm only going to get to pick 0. And the formula to calculate this is actually kind of cool. So you put the total number of things you have on top. Those are all the different combinations. You get 5 things. And then in the denominator, you take the number of things you're choosing times the number of things you're not choosing. So you kind of put them into 2 groups. So you can see here that the 5 factorials cancel, and you end up with 1 over 0 factorial. So this is like the only time in math where it is legitimate to see a 0 in a denominator, because there's a factorial attached to it. And 0 factorial is 1. For the same reason that anything raised to the 0 power is 1. Okay? So this works out to be 1. There's only one way. Right? But what if I told you you get to pick 2 candy bars? So you would say, well, we have 5 candy bars. I'm choosing 2, so that means there are 3 left I'm not choosing. So if we look at this, well, the numerator, right, is 5 times 4 times 3 times 2 times 1. The denominator is 2 times 1 times 3 times 2 times 1. So the 3, 2, 1 cancels, and you just get 20 over 2, or 10 ways. So there are 10 different combinations of 2 candy bars you could get out of a bag of 5. So this is a fun little party trick. I just like showing it to you guys because it's just some neat problems where we can play with factorials for a second and kind of get comfortable with them. All right, so the general formula of this is we say n choose k is n factorial over k factorial, right? The number of things you chose times n minus k factorial. So these are the things you want, and these are just the things you didn't want. That's it. Just put them in the 2 baskets. What's really wild is there's a multinomial theorem, right? Which says, what if I had 20 things in a bag, and I want to split them up into groups of 3, 2, 5, right? I just need to make sure the things I'm choosing add up to 20. And so then the formula is augmented where you take the 20 factorial here, and then you multiply by all the different baskets you're going to divide the things up into, and that will tell you the total number of ways it can happen. So it's actually kind of a fun thing. All right, so let's look at some useful properties for factorials. We're going to use these a lot. And like once you know how they work, they're pretty easy to work with. And one of the things you new folks are going to learn is you're going to need a thick notebook. We take lots of notes. All right. So we already talked about 0 factorial is 1. Hopefully it's kind of intuitive, right? That the limit as n goes to infinity of n factorial is infinity. And similarly, the limit of 1 over n factorial should go to 0, because that's just 1 over infinity. Now, there's some notation I want to make sure you guys get down, because you can have coefficients in front of factorials, but if you're not reading the problem right, you'll put the coefficient in the wrong place. So, c times n factorial is actually read as c is on the outside times the factorial. So if I had 2n factorial, it's 2 times, I could pull the 2 out in front of the limit. All right? However, if I attach the constant to n inside parentheses, well, now what I'm saying to do is start at 1 right? Multiply all the way up till you get n, but c times n is going to be bigger than that, right? So then you keep counting up to whatever integer c to the n is. So we can look at these two properties with some real numbers. So let's compare 2n factorial versus 2n quantity factorial. And let's let n equal 3. So 2n factorial is 2 times 3 factorial. So it's 2 times 3 times 2 times 1. And that's just going to be 2 times 6, which is 12. So notice if I don't know the value of n, I start, when I write the factorial and I expand it, I start at 1 and I count up to n. But if I do know the value of n, you start at that value and go down to 1. That's just kind of the way we do it. Because if you try to go n down, it's really awkward because you don't really know where you started, so you don't really know where to stop. So that's why we kind of write it backwards. All right, but if I have 2n quantity factorial, well, 2 times n is 6. That's really 6 factorial. So that's 6 times 5 times 4 times 3 times 2 times 1, and that's 720. So very, very different answers from that notation. So what we also need to know about factorials, and this will be a good place, we'll do this last little bit and then we'll be a good stopping point for today, is how do factorials compare to other things we know that blow up to infinity? So we're all pretty confident that exponentials grow faster than polynomials. We actually saw a L'Hopital problem, right? So I would say we're all pretty sure that factorials are probably going to grow faster than power functions, right, or polynomials. But how do factorials and exponentials compare to each other? Because they're both very, very fast-moving things. So let's look at that. So how do exponentials compare to factorials? So what we're going to look at is 2 to the n versus n factorial. So let's make a table. And let's see what happens. So I'm going to start at 1. 2 to the 1 is 2. 1 factorial is 1. When n is 2, 2 squared is 4. But 2 factorial is just 2, because it's 2 times 1. When n is 3, 2 cubed is 8, but 3 factorial is 6. 3 times 2 times 1, right? When n is 4, 2 to the 4th is 16, and 4 factorial is 24. So notice, it looks like the exponential's winning early on, right? But then look what happened here. The factorial overtook the exponential. So let's look at 5 and 6. So 2 to the 5th is 32, 2 to the 6th is 64. 5 factorial is 120, and we already saw just a second ago that 6 factorial is 720. So this is what I was getting at earlier. Once you cross the 4th term of the sequence, if these were 2 sequences we were looking at, the factorial overtakes the exponential. So when they're small, factorials get really small, and then they start growing very rapidly. And so for this particular comparison, we would say that n factorial is greater than or equal to 2 to the n for all n greater than or equal to 4. So the 4 here is the capital N I was mentioning earlier. So even though early on they behave a little strangely, and sometimes you'll even see things that crisscross a couple times, but then there's a tipping point where one of them takes off like a rocket and leaves the other one in the dust. And that's what we care about because we're only looking at stuff as it goes to infinity. So we'll write one more little quick note and then we'll call it. So we can always find an n, for which n factorial will overtake c to the n as n goes to infinity. And so my kind of little way of thinking about it is factorials dominate exponentials as n goes to infinity. Sorry, my bad.